Oh, my quote of the day copied over to the wrong spot. There we go. All right, so the plan for today is just to talk about the next integration technique, partial fractions. Note the Unit 1 exam on Chapter 6 and 7 is the week of the 19th, and I posted the Examity practice exam along with an announcement kind of detailing a lot of information about that exam. A couple of kind of high points is the only purpose for this Examity practice exam is for you to practice going through the Examity structure. So to log into Examity, start the session, log into WebAssign, start the exam, have Examity enter the password so that it's password protected, just so you don't accidentally start the actual exam outside of the Examity environment. So go through, complete the exam, close out the exam, close out the Examity session, and so on, so that you have a chance to go through all of that, make sure that you understand everything, make sure that you've experienced it once so it's a little less stressful, and make sure that all the tech is working out and everything before it comes to the actual exam. So the Examity practice exam doesn't count for any credit or anything like that. It's just for you to be able to practice that process. There are a couple of calc questions in that exam, but again, like, it doesn't matter if you get them right or wrong. I didn't pick questions with the thought that like you should be able to do these in 15 minutes or anything like that. So if you don't feel that there's enough time, like, none of that really matters. The important thing is that you go through the Examity process, get into the exam, make sure everything kind of works, you're able to submit stuff and all that, close out of the exam, and so on. And it's really about just practicing that process. Roughly a week before the exam week, so sometime this upcoming week, I'll post a sample exam. And the purpose of that sample exam, it won't be locked down, you won't take it through Examity. But the purpose of that sample exam on WebAssign will be for you to actually practice the material. So it'll be an exam that's very similar to the actual exam, the actual Unit 1 exam. And it will be, a similar length, similar difficulty of problems, similar types of problems, and similar assortment of problems, so on. So that practice exam, is meant as a study tool. And when that practice exam is posted, my recommendation really is to sit down as though you were taking the actual exam in the same environment, with only the resources that you'll have on the actual exam. Sit down and take that practice, or sorry, take the sample exam as though it were the actual exam. Time yourself, give yourself the same time as the actual exam, and then see how you did at the end. If maybe you got stuck on a certain problem or a certain topic, or maybe if there was a topic that took you a lot longer to do than you thought that it was going to, maybe either go back and review that topic or adjust your test taking strategy. Maybe if you say, oh, this problem, I'm just not so quick at that type of problem, maybe you leave that until later in the exam or something, and skip over, come back to it or something. So I would use the sample exam as an assessment of kind of how strong you are in different areas. Maybe there are some areas you want to strengthen a little bit, or maybe there's a change to your test taking strategy you might want to make as a result of that. And then, of course, the exam will be open that whole week. So you'll be able to schedule your Examity time, get in, take the exam through WebAssign anytime that week that's most convenient for you. And of course, as I said a couple of times in the syllabus, and I'll say again in the announcements, do not wait until the last day to take the exam. There are no due date extensions because it's open for a full week, so give yourself some margin. Try to take it sometime during the week so that there's more help available, there are more options available. If you wait till Sunday night, that cuts your options pretty significantly. Okay, are there any questions on any of that administrative stuff? All right, and then the quote of the day from the Roman lyric poet Horace in his work Satires is a rough translation. There is a mean in all things, too far to the right or left of which good cannot be found. So keeping things in balance is usually a good a good strategy for academics as well as life. All right, so partial fractions. So let's do an introductory problem, and then we'll take a look at the strategy of partial fractions, the integration technique, partial fractions. So let me zoom this in a little bit. There we go. So I have this integral that I want to do here, integral of 1 over x squared minus 5x plus 6. I'm integrating a rational expression. And I've seen before that sometimes things like integral of 1 over 1 plus x squared, that might be like arctan x. Integral of something like, 1 over square root of 1 minus x squared, or x squared minus 1 might be some kind of arc sine or arc hyperbolic sine, or, some of these kind of trig type results. But I don't recognize this right away as something that a trig substitution is going to help with. Mainly the reason is the mixture between the linear component and the quadratic component. If I just had a quadratic, I'd be thinking something like an arctan, maybe using a trig substitution like that. If I just had a linear, of course, here I'm thinking of a log, natural logarithm of some sort. But I have this combination of these two. So how do I approach this? Well, one thing I might note is that x squared minus 5x plus 6 can be factored. And therefore 1 over x squared minus 5x plus 6 is 1 over x minus 2, x minus 3. Now, maybe this didn't get me very far, but if I look at this and I say, well, could this be something like 1 over x minus 2 plus 1 over x minus 3? Could this fraction break into some partial fractions like this? Well, I note that if I combine these together, my common denominator is this x minus 2, x minus 3. So what would this give me? This would give me x minus 3 plus x minus 2 over x minus 2, x minus 3. It doesn't quite work out, but I actually see that if I made this negative, then I'd have 3 minus 2, which would be 1, and my x's would go away. So if I made this negative, if I made this a negative 1, then these would all be true statements, right? So this gets to the point where I have negative x plus x, they go away, plus 3 minus 2. I've recovered my initial fraction. So in other words, I could break this into the integral. Let's write it as 1 over x minus 3 minus 1 over x minus 2 dx. Now, what's the benefit of doing this? Remember I said that if we had only a quadratic term, we could maybe do some kind of trig substitution. If we had only a linear term, we could recognize that as a log. Well, the integral of the difference is the difference of the integrals. And this I recognize as log absolute x minus 3 minus log absolute x minus 2 plus c. Or maybe I want to combine these as log absolute x minus 3 over x minus 2 plus c using one of my log properties. So this is the idea of partial fractions. The idea is we want to do kind of a fraction decomposition of a complicated fraction, a complicated rational expression, into simpler fractions that I can maybe recognize as either kind of trig substitution. Well, saying that kind of grammatically strangely, I can recognize as either integrands that are amenable to a trig substitution or as things that look like a logarithm. Okay, so what is the general strategy? So first off, if the degree of the numerator, here I have a partial or a rational expression, if the degree of the numerator is bigger than the degree of the denominator, then we want to do polynomial division until we get a new numerator where the degree of the new numerator is less than the degree of the denominator. So up here, we had a numerator that was degree 0, just a constant, denominator that was degree 2, so the degree of the denominator was bigger than the degree of the numerator. We didn't have to basically break off any polynomial terms. But if this was the case, if the numerator had a larger degree than the denominator, we could break off a polynomial component, some 3x squared minus x plus 1 or something, and then of course we know how to integrate those polynomial terms with no problem. And then we would have a remainder where the degree of the numerator is less than the degree of the denominator. So once we have a situation where we have a rational expression with degree of the numerator less than degree of the denominator, then we factor the denominator. We know that by the fundamental theorem of algebra that this polynomial that's in the denominator, again, we're thinking of rational expressions here, so this denominator is a polynomial. It can factor into linears and quadratics. It'll factor into linears for any of our roots of that polynomial that are real roots, and into quadratics for any roots that are complex roots. Then we want to construct a decomposition. And this looks kind of complicated, but basically what we're saying is if I factor my denominator and I get px plus q to the m power as a factor out of it, then I want to take one constant over px plus q to the first power, plus another constant over px plus q to the second, and so on until I get to px plus q to the m power. And for the quadratic bits, why did I use a constant on the top here? Because that's a lower degree polynomial than the linear on the bottom. For the quadratic bits, ax squared plus bx plus c to the n power. I start with ax squared plus bx plus c to the first power in the bottom. And then I want a lower degree polynomial in the numerator, which would be a linear b1x plus c1. Similar thing with the quadratic to the second power if needed, with the linear on top, and so on. Now, practically speaking, for any of these we're doing by hand, we're probably only going to get like a quadratic to the first power at most, or maybe a linear to the second power at most. Anything more than that becomes just incredibly computationally complex, and doing it by hand really isn't feasible. Even if you understand all of the calculus, by the time you get to the end, you'll have made some goofy little sign error, goofy little arithmetic error, and you'll never be able to carry out that many steps in a row perfectly. So at that point, if you're up to where m is 5 and n is 4 or something like that, you're going to use a computer or something like that to do it. But let's take a look at this next one. So this is one where we have a couple extra steps to do. We note that the degree of the numerator is bigger than the degree of the denominator. So the first thing I'm going to do, I'm going to kind of come off to the side here and do a bit of polynomial long division. So I want to divide my numerator polynomial by x squared plus x minus 2. So I take my leading term in the divisor, x squared. How many times does it go into 2x cubed? It goes in 2x times. 2x times x squared is 2x cubed. 2x times x is 2x squared. And 2x times negative 2 is minus 4x. And that'll get subtracted, just like usual on division. What I like to do here, because it's super easy to make a little mistake here and kind of throw off the entire problem, I'll make this a plus, this a minus, this a minus, and this a plus. Just distributing that negative so I don't forget about it on those later terms. These go away. I've gotten rid of my cube parts. X squared minus 2x squared is negative x squared. Negative 7x plus 4x is minus 3x plus 7. X squared goes into negative x squared how many times? Minus 1. Minus x squared minus x plus 2 with a negative. And please check my arithmetic as I'm going along here. Super easy to make an arithmetic error here. If you see anything that I goofed up, definitely let me know. So plus, 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 and minus. My x squared terms go away. Minus 3x plus x is minus 2x. Plus 7 minus 2 is plus 5. So I have my quotient plus the numerator of the remainder over the denominator. I haven't done any calculus yet, although this is, somewhat annoying algebra. So this rational expression can be rewritten as 2x minus 1. Note that the degree of the numerator was 1 above the degree of the denominator. So I'm able to break off a linear and a constant component. And then plus a negative 2x plus 5 over the denominator. But I think I'm going to write that as a minus 2x minus 5 over the denominator. And then I'll cross my fingers and hope I don't forget that, that minus at the end. Okay, so if I want to integrate r of x dx, well, my first step is to handle the polynomial term. So integral of 2x is x squared minus x minus, we'll put a question mark there. We might need a little more room for that. And then plus c. And this is where the rational or the partial fractions really comes into play, dealing with this bit here. So we made one step forward. Now we're going to come back over here. Maybe switch colors. And we'll deal with 2x minus 5 over x squared plus x minus 2. So if I look at this denominator, I see that minus 2 is plus or minus 1 times 2. And if I do x plus 2 times x minus 1, that seems to work out. let me take a peek back at my general strategy, and I see that I have now two factors, each of which is a linear to the first power. So decompose this as two pieces that look like this. I'll have number over x plus 2 and plus number over x minus 1. So I have a first linear to the first power and a second linear to the first power. Each of those is going to contribute a constant over its linear piece. So this is really the partial fraction step. Number one, the claim that I can do this, the claim that this will work out. And number two, the method of doing this. So if I focus on just this bit here now, I say, okay, how can I actually figure out A and B? That's not really a trivial task, right? But one thing I could do is I could multiply through by x plus 2 times x minus 1. Putting an x for multiplication looks like an x for the variable, so I'll just put a dot here for the times. And this would give me 2x minus 5 equals a times x minus 1 plus b times x plus 2. Okay, so I have a simpler relation between these bits. And there's kind of two approaches I can take here. I'm going to go through both of them. I was going to call it method A, but we'll call it method 1 because we've already got an A floating around. So method 1, I know that with polynomials, if I have polynomial equals polynomial, because like the constants are like terms, the linear bits are like terms, quadratic bits are like terms, but quadratic bits aren't like terms with any of the linears or constants or anything like that, right? The different degrees of the polynomials are different terms. They're unlike terms. So that means that if I have a constant term on the left and a constant term on the right, they have to be equal. If I have a linear term on the left and a linear term on the right, they have to be equal. Or in other words, their coefficients have to be equal. Oh, so I can look at, I've been having trouble all day with my trackpad jumping around like that. And so I can look, for instance, at the linear terms. On the left, the coefficient is 2. And on the right, the coefficient is going to be a plus b. Right, on the right, if I multiplied this out, I'd have a plus b x, and then plus 2b minus a. My constant terms are going to be that negative 5 equals 2b minus a. I have a 2 by 2 system to solve. It seems like if I just add these together, that'll work pretty well. Negative 3, a minus a goes away, equals 3b. B has to be negative 1. And then a plus 2, or sorry, a plus b is 2. A has to be 3. So this linear system wasn't too bad to solve because my coefficients worked out pretty nicely. Method 2, I guess I'll do method 2 in red. So method 1 is matching up like terms on either side of the equation. Another way that you can think of why that has to be true is I could just subtract everything over onto one side of the equation, combine all my like terms, and then to make that whole left side equal 0, all of my coefficients have to zero out. So that's another way that you can really convince yourself that what I'm saying is true, that you can match up linear coefficients, constant coefficients, quadratic coefficients on either side of the equal sign. So if you weren't wholly convinced by what I said before, you could think of it that way. Method 2 is kind of a guess and check kind of idea. So I could choose a particular value for x, maybe say x equals 0, and I would get some number on the left side, -5, equals something with a's and b's on the right side. Right? X equals 0, or substituting in x equals 0 would really just be pulling out my constant terms. That just makes all of the linear, quadratic, etc. terms go away. I could substitute a different value for x. In fact, I might choose a value for x to substitute like x equals 1. I choose this because that makes this term go away. That gets rid of a altogether. If I plug in x equals 1 on both sides, I have 2 times 1 is 2 minus 5 is -3. The a times x minus 1, well, that's 1 minus 1 times a, that's 0. I have b times 1 plus 2 is 3. And I see that b has to be -1. And then the other choice I might make for x is x equals -2. This will zero out the second term with b in it. If I plug this in on the left side, I get -4 minus 5 is -9. And on the right side, I get a times -2 minus 1 is -3a. Says that a has to be 3. I get my same answer either way. In this problem, the linear system was easy enough to solve and the substitutions were easy enough to figure out. It probably doesn't really much matter which way I went. Sometimes I think one way would be preferable to another. And for more complex problems, sometimes it's super helpful to use a combination of the two. Maybe use a couple of substitutions to knock out, maybe if we have A, B, C, D that we're trying to figure out, maybe we use a couple of substitutions to knock out a couple of the numbers, and then we use a linear system to figure out the last two or something like that. One little side note, you might be saying to yourself, wait, we plugged in x equals 1 and x equals -2, but if I think back a couple of steps, aren't those like restricted values, right? Well, keep in mind with a rational expression like this, that these we've kind of cleared those zeros out of the way. This does end up working out just fine. I mean, in some sense, you can a little bit think of it like, if there's a hole here or something like that, we can just kind of imagine, say, roughly filling in the hole. You could think of it a little bit along those lines. Basically, it turns out that it works okay. We're not trying to plug in x equals 1 or -2 up here. We're doing it down here solely for the purpose of finding a and b. So we're just basically we're equating the numerators up here and then just figuring out what a and b is going to work. So we're not like saying that we can plug them into the original rational expression or plugging them into the integral or anything like that. We're using this just as a step to help us find a and b and help us solve the integral. Okay, so I have, again, this rational expression that I want to integrate. I can break it down into partial fractions. And then I see a has to be 3. And then b, be -1. So I can integrate this instead. And I see that the integral of my rational expression dx if I go through and do this integral, I get 3 log absolute x plus 2 minus log absolute x minus 1. Or maybe I'll combine that with some log properties. Something like this, I think, is probably the tidiest form for it. And let's see if I can lasso select this. OneNote hasn't been super cooperative today so far, but I think I might have missed an absolute value, but oops, and I have my question mark there. But all right. I think I might have missed a couple pieces, but that's x plus 2 cubed over x minus 1. That looks good. So again, several components to this. First, we check, is the degree of the numerator less than the degree of the denominator? If it's not, if it's equal to or greater than, do polynomial long division, break off my polynomial terms, and then integrate those. Those are straightforward to integrate. And then I'm left with a rational expression that's the remainder, in a sense, that where the degree of the numerator is less than the degree of the denominator. Then I go ahead and factor my denominator, break my rational expression into its kind of candidate partial fractions. Again, according to these rules. And I say these are candidate partial fractions because we could have ended up with like b equals 0 or something. Not really in this case, but in a more complicated case, we could end up with some of our, if we had a, b, c, d, for instance, maybe c would be 0. So we might not actually see all of the fractions end up in the final answer, but we want them all there just in case. But we have our candidate partial fractions. We go through and using either kind of this linear algebra approach, solving the linear system, or kind of a guess and check type of approach, being creative about what values of x we input to help us solve, or a combination of the two if we have a harder problem, figure out what a and b are, and then hopefully at that point we've gotten ourselves down to a series of integrals that we can compute pretty straightforwardly, either as logs or maybe as something like arctan, or maybe a slightly more complicated version of arctan. Are there any questions so far? Any questions on this problem? So there's definitely a lot of steps to a problem like this. Most of the steps are pretty straightforward if you kind of understand the overarching strategy. But every step, even the polynomial long division, that's, I guess, technically like a MAT202, level material, although it's a pretty challenging topic in that course. Even this polynomial long division it's simple. It's a simple idea, but carrying everything out, not dropping any negatives, is pretty challenging. So I think one of the important things with partial fractions, and really a lot of these integration techniques, is just kind of the bookkeeping, doing all of the arithmetic right. It's so easy to get caught up in the calculus and then make an arithmetic flub and get the whole thing wrong. Doing the arithmetic right, doing the algebra right, just being super careful with things. And then also making sure that, in something like a substitution, that we're using everything in the integrand, nothing that's not in the integrand. Or in something like this, making sure that we just take that initial step of breaking off that polynomial component before we try to jump right into partial fractions. If we try to jump right into partial fractions from here, it might feel like we could just jump right into a over x plus 2 plus b over x minus 1, but really, because the degree of the numerator is not less than the degree of the denominator here, we have no reason to expect that the degrees of these numerators ought to be less than the degrees of those denominators. So a lot of bookkeeping, just a lot of being careful with these little details. Okay, next example. Use partial fractions to integrate this rational expression. And also, because these problems just take a while to do, I will post a supplement going through a couple more of these. So I know that these take a while to do, and you don't get to drill a whole lot of them. Okay, so here my denominator is a 4th degree polynomial. My numerator is a 3rd degree. So degree of the numerator is less than the degree of the denominator. So we can move right into partial fractions. I want to factor my denominator. And I note that x squared plus 4 doesn't factor into the reals. But x squared minus x does. So no more factoring for x squared plus 4, but x squared minus x is x minus 1. Okay, so I have 2 linear factors and 1 quadratic factor. Again, the linear factors each get a numerator that's a smaller degree, so a constant. The quadratic factor, we got to be careful. It gets a numerator that's a smaller degree, so a linear. We need to remember to include that linear term for that quadratic factor. Okay, so I want integral r of x dx. And again, I'll come over to here and do my partial fractions work. I don't want to have to keep writing integral and dx and all of that. Okay, so this rational expression is equal to, we have over x for our first factor. That's a linear. I'll put a constant on top that's 1 degree smaller. X minus 1 is the next factor. That's a linear. 1 degree smaller is a constant. X squared plus 4. That's a quadratic. 1 degree smaller is a linear. So don't forget that CX term on the top. Again, just all these little details, one little misstep here or there can throw the whole thing off. Okay, so we did get that CX up there. I can multiply through. I can multiply through by my whole denominator over here. And then when I multiply through by x, the x's divide out, but I'm left with an x minus 1, x squared plus 4. For the b term, the x minus 1's divide out. And I get 1 of each of the other factors. I might even need a little more room here. Cx plus d, my quadratic piece divides out, but I get x minus 1. Okay, so I can maybe start substituting in x equals 0. On the left, that gives me -8. On the right, that gets rid of this term because it has an x, as well as this term because it has an x. So that gets rid of the B, C, and D pieces. And I just get A times -1 times 4. -4A equals 8. A equals 2. Okay, I've got 1 taken care of. X equals 1 seems to be a pretty good value to substitute in as well. That'll knock out the A term as well as the C and D term. On my left side, I just get 2 minus 4 minus 8. So 2 minus 12 is -10. Again, if you see, if I make an arithmetic flub, please call it out. But I'm trying to be pretty careful and go fairly slowly and methodically through this. -10 on the left, -12 plus 2. On the right, for x equals 1, my A term goes away. My B term is B times 1 times 5. And then my C and D pieces, that x minus 1 cancels those out as well. 5b equals -10. B equals -2. Okay, so I've gotten A and B. I need to get C and D now. One thing that I notice about C is that C is the coefficient of a cube, right? I get Cx times x times x. Well, maybe if I match my cubic terms, or really my cubic coefficients. On the left, I have a coefficient of 2 for x cubed. On the right, what do I have? A times x squared is just A. B times x squared is just B. And then for the cube part, D doesn't come in at all, right? I have C times x times x times x, so that's plus C. And D actually doesn't factor in at all because D at most multiplies an x squared. D never makes it to the cubic term. I know what A and B are. 2 equals 2 minus 2 plus C. Those go away. So C equals 2. And then what could I do here? Well, I could pick maybe x equals -1 or something like that, or x equals 2 to try a different value of x. I don't want to match up constants because that's effectively what I did when I picked 0. So that kind of leaves me with, and I don't really want to do -1 because that's a lot of negatives. I'll probably make a mistake. I don't really want to plug in 2 because I have cubes and squares floating around. That seems unnecessary to go through all that calculation. What about a linear or quadratic? Well, I noticed that I have a dx squared. So I have a linear component there. I also notice on the left side, my coefficient of x squared is 0. Maybe I'll match up quadratic coefficients. That seems like it might be a good approach for this problem, right? Lots of approaches. I'm picking the one that I think is probably going to work out pretty nicely. If you picked a different approach, and you were careful with the arithmetic and so on, you should get the same answer. The quadratic coefficient on the left is 0. On the right, what's the quadratic coefficient? Well, so what does A multiply? I have an x against an x squared or against a 4. That gives me a cube or a linear. So no contributions to quadratic from this x. But A times -1 times x squared, that gives me -A as the coefficient of x squared from that first term on the right. What about my B term? Well, my x either multiplies an x squared, giving me a cube, or a constant, giving me a linear. No contribution to the quadratic coefficient from the B term. And I might be, a little excited and just jump to plus D here, but I got to be really careful. Do I have a contribution from this term? cx can multiply x and then multiply -1. So I do get a negative c or minus c coming in as a contribution to the quadratic term. And then I have plus d. Negative a minus c, or in other words, d equals a plus c, I guess we could say. So d equals 4. So that's our a, b, c, and d. As an aside, just kind of something somewhat tangential, is we could have gotten maybe say in a different problem like c equals 0, and for that particular problem maybe we didn't need a linear above this x squared plus 4, but we see that for this problem we have c not equal to 0, so it was very important to include that to include that linear component. If I didn't include that, I would have gotten an answer that was wrong. Okay, so after all of this, I want to integrate a over x, 2 over x, plus b over x minus 1, minus 2 over x minus 1, and then plus cx plus d, 2x plus 4 over x squared plus 4 dx. This is still not an easy integral to do, but it's hopefully a bit more manageable. So I see this as integral 2 over x is 2 log absolute x. That's not too bad. Minus 2 log absolute x minus 1. Again, not too bad. I just have to be a little careful here. If I had like a 3x minus 1 or something, I'd have to make sure to take care of that substitution, or fix my constant, my coefficient. So let me come off to the side and work out these, or this last term of the integrand, which will split into 2 integrals. Okay, so I have a linear over quadratic. This feels like a log. Linear over quadratic. Does this end up just being log of x squared plus 4? If I differentiate that, I get 1 over x squared plus 4 times 2x. So the 2x on the top does kind of work out with that, but the 4 doesn't quite work out. So I'll just split those up. Like this, and now I do see that I have log x squared plus 4 here. When I differentiate this, I get 1 over x squared plus 4 times the derivative of the inside is 2x. So that works. X squared plus 4 is always positive, so I don't need absolute values here. I could put them on, it wouldn't hurt anything. And now I need to integrate this. And this looks a lot like an arctan, but I just need to fix the constants. I can divide top and bottom by 4. X squared over 4 is x over 2 all squared. So I get 1 over 1 plus something squared. Here I am going to be a little careful. There's just a lot going on here. So dx is 2 du. And then I have 2 du. This gives me 2 arctan u, or 2 arctan of x over 2. So I have like mini problems inside of mini problems inside of mini problems. So that is what this integral turns into. And where did my original integral go? Almost completely disappeared. So I'll just append these bits onto the answer up there. And then, as always, we'll toss a plus c on at the end. I suppose we could do a little bit of combining here. So I actually don't think I need an absolute value. I could do log of x squared, put this 2 up in the power, minus, so divided by inside the log. And then put this 2 in that power. And then plus, so times inside the log. Since all of these bits are, these are squared and that's positive, we don't need parentheses, or we don't need absolute values. We can just use parentheses. And I suppose this is what we end up with. Something that I kind of ask myself, and this is very heuristic, this isn't, really, this isn't like some theorem or something like that. But when I get an answer like this, I ask myself, does this kind of make sense? I see things like log x is the type of thing that I get out of this integral. That's maybe in a sense the leading term, something like that. In the sense that log x, as I go off to the right, shoots off to infinity, arctan hits a horizontal asymptote. So that log x is kind of bigger in some sense than arctan. Again, this is all very heuristic. If I have a cubic over a quartic, my denominator is 1 more than my numerator. That feels like that integral is, like, morally speaking, a log, like a log x. And that is kind of, morally speaking, what I get out of it. I mean, this is something that I like to do. I like, just as kind of a check for myself. Does the result kind of feel like it's in line with what the integrand, with what I would expect from the integrand? I've seen a lot of integrals where I have degree of the numerator is 1 less than degree of the denominator, and they tend to look like logs. And, before all of the simplification and all that, that's really what I get out. So this kind of feels right. Again, it's not like, that's certainly not a definitive check that, like, yep, this is absolutely the right answer, I've double checked it, but it feels right. If it didn't feel right, I probably would go back through and just kind of double check all my work, make sure I didn't make a little mistake somewhere, anything like that. Make sure I didn't do something like, forgetting a linear above a quadratic denominator or something like that. Make sure I didn't flub a substitution or anything. But this feels right. This should be the right answer. And again, these partial fractions problems, they just do take a while. How much proper calculus did we do? Not a whole lot, just at the very end, right? Most of it was doing the factoring, solving the big linear system, solving the, essentially 4 equations and 4 unknowns, right? We have an equation for the constants, the linears, the quadratics, and the cubics, in a sense. So solving this big 4x4 system and maybe finding creative ways to make it a little less tedious than solving a true 4x4 system. And then at the end here is when we had to do the integration, the calculus, but we're not really introducing any new basic integration ideas, but this is a way to use this algebraic idea of breaking a bigger fraction into its component partial fractions so that we can more directly use the integration techniques that we saw before, whether that be something like trig substitutions, more or less. I mean, this we just recognized as an arctan, so we didn't need to officially do the substitution, or whether that's logs or just basic substitutions. We can more readily access those in the partial fractions than in the original, more complicated rational expression. Any questions on partial fractions?